So in this video, we're going to talk about an inflection point. So the point of inflection is a point on the graph of x or f at which the concavity of f changes. So maybe we change from concave up to concave down or vice versa. So this part here looks like the concavity here is concave down. So the second derivative is negative on this part of the curve. And then this part over here looks like the second derivative is positive. We're smiling, right? So that means that we are concave up on this side of the curve. And so a point of inflection would be the point at which the concavity changes. So that point right there is the point of inflection off of that picture that you can see right there. Okay? Now, theorem. So I had a definition of concavity or inflection point. Now I'm going to do a theorem for this. So if c comma f of c, which is this point of inflection right here, if this value here is c, that's c comma f of c, okay, is a point of inflection on the graph if the second derivative is 0 or the second derivative is not defined at c, okay? So that's the case if the second derivative is 0 and or not defined at c. Now, what this is not saying is that if the second derivative is 0 or does not exist, then we have an inflection point. That is not the case, okay? So we talked about this in other videos. If P is true, then Q is true is not the same as if Q is true, then P is true, okay? So this is what's known as the converse of that first statement there. So those aren't the same thing. So if the point of inflection is on the graph, then that means that the second derivative is 0 or undefined, okay? It doesn't go the other way. The other way just tells us potential points of inflection. So the converse is not always true. Now, talk about f double prime not being defined. What about if f of c is not defined? Well, and we've got some second derivative evaluated there does not exist, obviously, if the original function doesn't exist at that point. So this then x equal to c is not an inflection point. If it's not defined at the point, it can't be a point of inflection. If there's no point there, then how can you have a point of inflection? So an example here would be like this function, like 1 over x. So the second derivative of evaluated at 0 here is undefined, but that doesn't mean that we have an inflection point at that point right there, right? So there's no point at x equals 0. It's actually undefined there. Even though we're concave down here and we're concave up here, there's no point of inflection. So just because we change concavity from one part of the graph to the other doesn't mean there's a point of inflection there, because the point is not defined anywhere on that vertical line x equal to 0. Okay? All right, so let's work through an example. So we're given a function, and I want to find the possible points of inflection and then create a number line to determine the intervals where we're concave up and concave down. So we're looking for the possible points of inflection. So all the possible points are when the second derivative is 0 or undefined, okay? Because since if it is a point of inflection, then we know those to be true, all right? So here, let's take this polynomial. Polynomials are nice because they're defined for all real numbers, continuous and differentiable. So let's start taking derivatives. Derivative of x to the fourth This is just 4x cubed. Derivative of negative 13x cubed is negative 39x squared. Derivative of negative 21x squared, bring the 2 out front, it's negative 42 to the x. A derivative of 6x is just 6, and the derivative of negative 42 is just 0. Now, that's the first derivative, okay? We need the second derivative to tell where concavity, up or down. This tells us if it's increasing or decreasing. The second derivative tells us concave up, concave down. So the derivative of 4x cubed is 12x squared. Derivative of negative 39x squared is negative 78x, and the derivative of this is negative 42, and the derivative of that is 0. Okay, so what do? Well, I set the second derivative to be equal to 0 or not defined. Well, guess what? Polynomial, quadratic, a parabola here, this thing is defined everywhere, so that's not going to work. All we do is we set the derivative equal to 0. That's all we can do. So if I set it equal to 0, to solve this, I'm going to factor a 6 out of each one of those terms. If I do, that leaves me a 2 here. That's going to leave me, what, a negative 13 there, and then a negative 7 here. Okay, so that's where this comes from. Factor a 6 out of each term. Now I want to factor trinomial. I want to use the AC method. Okay, so I'll actually do this one for you because you may not be able to just do that right away. AC method takes the first and the last, multiplies together. 2 times negative 7 gets you negative 14. So I want to multiply to negative 14. I want it to add to negative 13. If I did that, multiply to negative 14, add to negative 13. Looks like negative 14 times 1. That'll work. So I'm going to take 2x squared minus 14x plus 1x minus 7. I'm going to factor a 2x out of this. I have x minus 7. I'm going to have, well, I can't take anything out of that except for 1. And so I'm going to factor that. And I use the AC method. I pull this out. X minus 7. What's left? 2x plus 1. So that's where these factors come into play. Okay? Delete all this real quick. Wasn't planning to do all the work for that. As always, you can go back to the factoring video in college algebra if you're still having trouble factoring. Okay, now what do I know? I set each piece equal to 0. 2x plus 1 equals 0. And x minus 7 equal to 0. And so that's going to get me negative 1/2 and x equal to 7. Okay, so just 2x plus 1 equal to 0. Solve for x. X will get you negative 1/2 there. And then same thing for x minus 7 factor, set that equal to 0. Don't worry about this one because 6 can never equal 0, so that's actually a contradiction. All right, so the possible points of inflection, we don't know for sure they are, but they're possible ones. Those are the possible points of inflection. And now I'm going to create a number line to figure out the concavity where we change from concave up, concave down. If I have 2 points, I'm going to mark 2 points here. Okay, now I need to pick points in between the points of possible inflections. And to do that, I'm just going to pick negative 1 over here, 0 here, and 10 here. There's no special magic to these numbers. I could have picked a 1. That's perfectly fine to pick 1 because I just need some number between negative 1/2 and 7. I could have picked 5. I mean, whatever. I think 0 is just an easy one to pick whenever I plug it into a derivative. So I'm going to plug in negative 1 into my second derivative here. Now, I'm going to look at the factored form. That's going to make it easier whenever I'm plugging in numbers because all I care about is it positive, is it negative, is it 0? So if I plug in a negative 1, I'm going to get 6, but I'm also going to get 2 times -1 plus 1, and then -1 minus 7. So that's 6 times, what is this? That's -2 and a +1. That's a -1, and then a -8. So that's a negative and a negative make a positive. Okay? So positive is greater than 0 on this interval here, so that tells me that we are concave up. We're smiling, right? This next one here, if I plug in 0, well, I get 6 here, but a 0 makes that go away, so that's a +1. And then 0 here, 0 minus 7 is a negative. Positive, positive, negative make a negative. And negative is less than 0, so I'm negative on this interval, so I'm concave down. I'm sad. Concave down is like a frown. Okay? The last one, I plug in 10 for my second derivative here, and whenever I plug that in, I get 6 times, well, 10 times 2 is 20, plus 1 is 21, so that's positive. Then 10 minus 7 is 3, which is positive. So this is definitely positive, and so I have concave up. All right, so now I can see my intervals for where I'm concave up is where I'm positive. So from -infinity to -1/2, and then from 7 to +infinity. Now concave down, this is where I'm negative. So I'm negative between -1/2 and 7. So the points of inflection, remember the definition says it's where we change concavity, right? From concave down to concave up or vice versa, and the point exists, right? Well, the points -1/2 and 7 exist for both of these because remember f is a polynomial and that's defined for all real numbers, okay? So points of inflection are -1/2, comma, and then I plug in -1/2 into my function here. So I'll literally take f of -1/2, and if you plug that into that nasty function up here, then you're going to get -777 over 16. Okay, yikes. In decimal form, it's like -0.5, comma, -48.5625. The other one has an x value of 7 because I'm changing from negative concavity to positive concavity here. And so it's -7, comma, and then I plug in f of -7. So I put a -7 in all those places for x, and it outputs -3087. Okay? Let's do one more example. Make sure we got this. So I've got a rational now. Now rationals I got to be careful about because remember rationals are only defined where the denominator is not equal to 0. So I set the bottom equal to 0. That's going to tell me that x equal plus or minus 1 is undefined at that point. So you're not going to have points of inflection there because it's undefined. Okay? Set this equal to 0, solve for x. So let's do the derivative. Let's just see if we can calculate the derivative here. So f prime, this is a quotient rule since it's a fraction. So I'm going to do low d high, derivative top is 1, minus high d low, okay? What is the derivative of x squared minus 1? That's just 2x. All over the denominator squared, okay? Now the top, we got x squared minus 1, and then minus 2x squared. So the 2x squared and the x squared combine to get negative x squared, minus 1, and then all over this here, okay? So now I'm going to take the derivative of this bad boy here, and so it's low d high, so low d high, the derivative of this numerator is negative 2x, okay, minus high, which is this here, d low, The derivative of the denominator, well, this has got to be a chain rule since I have something raised to the 2 power. I'm going to bring the 2 out front and subtract 1 from the exponent, but then I need to take the derivative of the inside. Derivative of x squared is 2x. So that's a chain rule inside of a quotient rule. And then the denominator, I square the denominator, and I get something squared. Squared is to the 4th. Okay, just make sure you understand if I have x squared and I square it, that's x to the 4th. That's where that 4 comes from. Okay. All right. Now, I can simplify this here. And so when I simplify, I'm going to factor out an x squared minus 1 from every term here. There's actually 2 of them here, and then there's 1 of them here. So I'm going to cancel that out with all 3 of those pieces. So that's why I have a 3 here and not a 4. Okay, so that leaves me with only one of the x squared minus 1 factors. And then I also still have this negative 2x. Negative, 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 those all cancel to make a positive x squared plus 1. And like I said, I'm going to cancel that out, so that just leaves me with the 2 and the 2x, which gets me the 4x here. Okay? I can simplify this even further. In the numerator, what do I have? Distribute. I get negative 2x cubed. My plus negative and negative make a positive 2x. And then this multiplies out to get 4x cubed and then plus 4x. And I can simplify. These combine and these combine so that I get 2x cubed plus 6x over x squared minus 1 quantity cubed. And I'm going to factor the numerator, okay? When I factor the numerator, I got a 2x pulled out and I have x squared plus 3 inside, okay? So kind of complicated, but work your way through, make sure you can calculate that second derivative. So now, what do I want? Well, I got to set the second derivative equal to 0 or wherever it does not exist. This one actually could not exist because, once again, this is a rational. And rational fractions, okay? Rational fractions, with a fraction, if the numerator is 0, then that's equal to 0. And with a denominator equal to 0, that does not exist, okay? So to figure out where the second derivative is equal to 0, I set the numerator equal to 0. And to figure out where the second derivative is undefined, I set the denominator equal to 0. So if I set the numerator equal to 0 right here, okay, I factored it just like I did here. And so what happens here? Well, this is a polynomial. It's x squared plus 3 is a parabola shifted up 3 units. It never crosses the x-axis, so that means this thing is never actually equal to 0, okay? So no real number can make this equal to 0, all right? However, 2x, if I solve this here, I have 2x equals 0. I have x squared plus 3 equal to 0, right? So nothing works here. X equal to 0 works here. So x equals 0 is our result from this. Okay? So once again, for it to not exist, I set the denominator equal to 0. So I'm going to set this denominator equal to 0 here. And so when I do that, I can take the cube root of both sides. Cube root of 0 is still 0. So I just have x squared minus 1 equal to 0. Well, guess what? This one is a parabola that's shifted down 1 unit. Well, this is negative 1 and 1 are my zeros here. Okay, if you wanted to solve, you'd have x squared equal to 1. Square root both sides, you get plus or minus 1. Okay. So these are the possible points of inflection. Now, before I go any further, I just want to make the point that, remember when we started this problem, we said that if the function was not defined at the point, then there's no way it could be a point of inflection. Well, guess what? X squared minus 1, if I plug in 1 or negative 1, that's going to give me dividing by 0. So I know that those aren't going to be points of inflection, but you need to be careful. Go ahead, they are possible points of inflection, but we know from algebra that we can't divide by 0 here, okay? So let's go ahead and list them all out on our number line. So I've got negative 1, 0, and 1, okay? So this is from my points of inflection here. And so I'm going to pick points in between them. So negative 2, negative a half, 1/2, and 2. Like I said, I don't care what point you pick as long as they are between on those given subintervals. Okay? If I plug in to the derivative, the second derivative here, so let me zoom in a little bit here. If I plug a negative 2 in here, what is that going to be? That's going to be a negative number first. Okay? If I plug in negative 2 here, well, what happens if I plug in a negative and I square it and I add 3? That's going to be a positive. And then if I plug in a negative 2 here, I square it, that's going to be 4 minus 1 is 3. 3 cubed is positive, so that's positive. So a negative number divided by a positive number is a negative. So if it's negative, it's concave down. Okay, concave down. The next one, negative 0.5. If I plug negative 0.5 in here, I get a negative times a negative is or negative times a positive is negative. If I plug in a negative here, but it's squared and I add 3, that's still positive. And then here is negative minus a negative. Okay, if I plug in a negative, that's a small positive, okay, because I'm squaring it. And then minus a bigger negative makes it all negative. Okay, if you don't believe me, just plug it in. Negative 1/2 squared minus 1, right? That's 0.25 minus 1, which is a negative something. I don't know what it is, but if I cube it, negative, negative, negative makes a negative here. Okay? We don't care so much about the numbers as much as the sign. So negative and a negative make a positive, and a positive makes a positive. Okay? So we're concave up there. Now, here, what's going on? I plug in 0.5, a positive, and then once again, I still have a negative. So positive divided by a negative is a negative number. So that's negative on this interval, concave down. Last one, I plug a 2 in to my derivative, and if I do a positive and a positive, that makes a positive. Positive squared plus 3 is positive. And then 2 squared is 4 minus 1 is 2. 2 times 2 times 2, that's a positive. So that's positive all the way around. Now, what you might be tempted to do is say, oh, look, down, up, down, up. 1, 2, 3 points of inflection. That's very tempting to do and could be a tricky test question, right? So what I'm looking for, though, is the point of inflection and not just the possible points of inflection. Now, why does negative 1 and 1 not work? Well, we talked about that, okay? It's not defined. F is not defined at 1 or negative 1. Can't divide by 0, folks. All right, however, F is concave up. It's concave up where the second derivative is positive. That happens to be between negative 1 and 0, and then from 1 to infinity. It's concave down from negative infinity to negative 1, and then from 0 to 1. Point of inflection is only here. Why? Because we are concave up here, but we're concave down here, and the function is actually defined at 0. If I plug a 0 in here, I get 0 squared minus 1. This is 0 over negative 1, which is 0. So that's where the 0, 0 comes into play. Okay? Since f is not defined for negative 1 or positive 1, then -1 and +1 here do not create points of inflection for us. Okay? And if you looked at this graph, x over x squared minus 1, okay, let's see if I can graph this. X divided by x squared, and then what did we say, -1? Oh, come on now. -1, close parentheses. Okay. You can see that the vertical asymptotes you have at -1 and +1, and then you can see here we're concave down here on this side, but we're concave up here on this side. So at 0, we switch concavity from positive to negative for that second derivative. Okay? All right.